Hello everybody, welcome back to Total Organic Chemistry. This first video will be a brief overview of some topics that are most widely encountered in general chemistry courses or at the very beginning of organic chemistry courses. I will cover some basic concepts with chemical bonding, drawing Lewis dot structures, and if I have time, orbitals and molecular orbitals, although if I don't get to those in this video, I will surely include them in the next. So for this set of videos and for this course in general, I'm going to assume a basic knowledge of general chemistry and most importantly, periodic trends. So things like electronegativity, atomic size or atomic radius, bonding, electron configurations, things like that. I will assume that you already know, or at least have a pretty good grasp on those concepts before you start watching these videos. Otherwise, it might be a good idea to take a look at some other resources online or some books to kind of get a grasp on that before you start jumping into organic chemistry, because organic chemistry is completely based on all of these different trends. So without further ado, let's jump into it. Chemical bonds are split into two main categories. There are others, but we're only concerned about two right now. You have covalent and ionic. And you might have heard of these before. Ionic bonds, I'll start with those, are when you have two ions, or two atoms, I guess, two atoms, and where one atom, completely transfers its electron to, or its electrons, to another atom. So if we have sodium, which has one valence electron, and chlorine, which has 7 in their ground states, you can transfer this one valence electron over to form sodium chloride, which is what we all know as table salt. Ionic bonds are very strong, and they usually form crystalline solids, like all these salts. Those are less important in organic chemistry. We'll use lots of salts and we'll discuss them throughout the course, but the bonding is relatively simple and not very interesting. So what we care most about are covalent bonds. Covalent bonds are when you have multiple atoms that share their electrons. So if we have a carbon atom, which has 4 valence electrons in its ground state, and then we take 4 hydrogen atoms, and neither of these really wants to, well, especially carbon, does not want to transfer its electrons at all, because that would make an extremely unstable carbon ion. So it's very difficult for carbon to either totally give up all 4 of its electrons or accept 4 more electrons to make a stable octet. Instead, we share the electrons to make covalent bonds. And this is methane, natural gas, CH4. And remember, this is also a topic from general chemistry, but like I said, this is a review video. So in all chemical compounds, the goal for our atoms, for our molecules, is to get everything with an octet. That means having 8 electrons around each atom. In the case of hydrogen, we call it a duet because hydrogen is very small, can only accommodate 2 electrons. So for methane here, we have carbon has, remember that each of these lines represents a chemical bond, which is 2 electrons. So we have 2, 4, 6, 8 around carbon here. And then we have around each hydrogen, we have the 2 electrons to make that duet. So covalent bonds can either be polar or nonpolar. So in the case of methane, each of these bonds is relatively nonpolar. What that means is that the electrons are shared relatively equally between the carbon and each hydrogen. How do we determine that? We determine that from the electronegativity of those atoms. So the difference in electronegativity from hydrogen to carbon is only about 0.4 units. So these bonds are all relatively nonpolar. So there's no significant dipole moment or shift in electron density between these atoms. So I'm going to write this delta about 0.4. But if we replace one of the hydrogens with a much more electronegative element, such as fluorine, the most electronegative element, now delta is now about 1.4. That's because fluorine is so much more electronegative, so it's going to pull those electrons in this bond much closer to itself than to the carbon. So what that creates is a dipole moment. We draw those a lot of times like this, with an arrow pointing towards the negative end, so towards the more electronegative element, and then with a little plus sign over here on the other side of the arrow that signifies that the carbon has a partial positive charge. We can also write that like this. We can write delta positive here and delta negative over by fluorine. So because of that, this is a polar molecule. And polar molecules often have much different reactivities than nonpolar ones. Another thing to recognize is the geometry of atoms, or of molecules, excuse me. So if you have something like CO2, which contains 2 polar bonds, so each of these C double O bonds, or CO double bonds, is polar. Oxygen is pretty electronegative. So we can draw our dipole moments like this. But you see that CO2 is actually a linear molecule. So those dipole moments cancel each other out. So carbon dioxide is a nonpolar molecule, even though each of its bonds are polar themselves. And how do we determine geometry in a certain molecule? The easiest way and the most common way is called Vesper theory. It's valence shell electron pair repulsion theory. And this tells us how do electron pairs move around, how do they disperse themselves within a molecule or around a single atom. So if we take our methane molecule again, it has 4 atoms coming off the central atom, carbon, and those electron pairs want to distribute themselves as evenly as possible over a sphere of 360 degrees, right? They want to be as far away from each other as possible because negative charges are going to repel each other. So we can draw that like this, where we have a wedge. Well, let's start with the regular lines, these bonds here, represent bonds that are in the plane of the paper. So this hydrogen and this hydrogen are both in the plane of the paper. You can imagine that just coplanar with the carbon atom. Whereas this hydrogen with the wedge, that bond is actually coming out of the paper towards you. And the dashed bond is going the opposite. It's going into the paper. So you can imagine that this CH4 molecule is a tetrahedron. All of the bonds are distributed so that they form a tetrahedron. And that makes an angle of about 109.5 degrees. So that's for 4 substituents around our carbon central atom. If we take another molecule, such as boron trifluoride, BF3 here, all of these bonds are in the plane of the paper because there are only 3 substituents around that boron. So this molecule is actually flat, or it's called planar. So this angle is 120 degrees, because those 3 substituents, the fluorine atoms, are arranging themselves in a triangle. We can also look at, again, our carbon dioxide molecule. And this time there are only 2 substituents around the carbon. So of course, we have a 180 degree bond angle now between those 2 oxygens. Because again, they want to distribute themselves as far as possible away from each other. And there are other geometries that exist, depending on how many electron pairs you have around the central atom versus how many total electron regions of electron density there are. But they're not extremely important in organic chemistry. And any deviations in these angles we can look at mechanistically when we look at reactions or processes in organic chemistry. So it's not extremely important to memorize all of the different combinations of electron pairs and electron pairs that are bonding around the central atom. So to show these molecules on a piece of paper, a useful formalism that we use in organic chemistry are called Lewis dot structures. And Lewis dot structures show the bonds around each atom, the bonds between atoms, and also the electron pairs that are called lone pairs around each atom, if there are any. And it shows us the structure, connectivity, and a lot of times the geometry of our molecules. So the steps for drawing these Lewis dot structures are as follows. First, we draw a skeleton of whatever molecule we want. So let's take H2O as an example. So what do I mean by skeleton? I mean a rough drawing of where the atoms are in the molecule. You don't have to have the geometry exactly right or anything like that, but we just take our oxygen, that's going to be our central atom, and then we know that the hydrogens are going to be connected to that oxygen somehow. If it's not immediately apparent where or which atom is the central atom, it will either be given to you or you will slowly and steadily get used to which atoms are usually central atoms in molecules like these. So we have our skeleton. Now we have to look at how many electrons we have to work with. So remember from general chemistry that valence electrons in atoms are those that participate in bonding. So oxygen has 6 valence electrons to start with. We can get that from the periodic table. And each hydrogen has 1, right? So we have a total of 8 electrons to work with. Those have to be eventually in our Lewis dot structures somewhere. Now we fill in our bonds. So we know that there's going to have to be at least one bond between each pair of atoms, right? Or sorry, between each atom and the central atom. So we know we're going to have at least single bonds. So we have an OH and OH bond. And how many electrons does that leave us with? So we started with 8 electrons. Now we have 2 plus 2, 1 from each bond. Remember, bonds are electron pairs. So we have 2 electrons for each bond. We just used 4 electrons total. We have 4 electrons left to use. Now, we need to use those electron pairs, those remaining electrons to form electron pairs or additional bonds. And remember, these always need to form octets. I shouldn't say always, for most cases. I will discuss exceptions to that shortly. So we know that we can't have any additional bonds because hydrogen can only accommodate 2 electrons around it. Hydrogen is very small, it can only accommodate a duet. That's the 2 electrons, so these bonds already accommodate that. So that means we have to have electron pairs somewhere, right? Those are going to be on the oxygen. We have 4 electrons left. We can put 2 electron pairs around that oxygen to make a full octet. That oxygen now has 2 electron pairs, that's 4 electrons, plus 2 from each bond. That makes a total of 8, and that's a full octet for the oxygen. And then full duets for the hydrogens. So this is our full Lewis dot structure for water. Let's do another example. Let's take formaldehyde, which is used in preserving bodies. It is relatively toxic as well. And I'm going to tell you that carbon is the central atom. So, draw our skeleton. Excuse me, I've drawn this HCHO. So we know that each of these atoms has to be connected to the carbon somehow. There's our skeleton. Now we have 4 plus 6 plus 1 plus 1 electrons from each of the valence electrons of the atoms. And that gives us 12 electrons to work with. So we can fill in our bonds now. We know that we have to have at least a single bond between all of these. Now we have 6 electrons left. We used 2 for each of these bonds. We have 6 electrons to work with now. So we can imagine filling those all in as lone pairs. Let's do that here. Remember that we need to make octets. So let's make 3 lone pairs around the oxygen and 2 around the carbon to make an octet. Now we have 2, 4, 6, and 8 around the carbon, and then 2, 4, 6, 8 around the oxygen. However, how many electrons does that leave us with total? We have 2, 4, 6, 8, 10, 12, 14 valence electrons now in our Lewis dot structure. So this is not a good Lewis dot structure. It uses too many electrons. We don't have that many to work with. If that ever happens to you, think about making a double bond. Remember, our hydrogens can't accommodate a double bond, so it's got to be between the carbon and the oxygen. Fill in our valence or our electron pairs to make full octets. Now we have 2, 4, 6, 8, 10, 12 electrons total. So this is our Lewis dot structure now for formaldehyde. Let me flip to the next page of my own notes. Another useful formalism when we're looking at Lewis dot structures and in organic chemistry in the future as well is called formal charge. And formal charge is a way of keeping track of where the electrons are. However, it is, like I'm going to say for a lot of things in this course, it is a formalism. And that just means that it's a way that we can communicate what we're looking at. We can communicate our ideas and reactions, but it's not necessarily the picture of how the physical world actually is. So it's important to keep in mind. So if we draw our Lewis dot structure for H3O+, this is hydronium. This is what happens when you put water and an acid together. Make our skeleton. We have 6 plus 1 plus 1 plus 1 valence electrons, and now we have a total charge of plus 1 across the entire molecule, so we need to subtract one of these electrons to make up for that. So that gives us 8 electrons to work with. We can fill in our bonds. One for each hydrogen, and then we have 2 electrons left to make a lone pair on the oxygen. Now we have an octet, and we have all of our electrons used. But now there is a charge that we have to keep track of, and that's called our formal charge. So to calculate formal charge, you take the number of valence electrons that an atom has when it's neutral, and subtract the number of electrons it owns in the molecule. So what does that mean? For oxygen, oxygen usually has 6 valence electrons when we just look at it on the periodic table, and it owns 1 and 2 right here, it owns, we can say it owns half of this bond, half of this bond, and half of this bond, right? So that gives us 2, 4, 5 electrons that are owned by oxygen, and that gives us a formal charge of +1. So we can communicate that. If we draw this out again, by making a small plus next to the oxygen. Now it shows us that the oxygen has a formal charge of +1. If we draw our Lewis dot structure for carbon monoxide, our skeleton, we have 4 plus 6 valence electrons total, so that's 10 electrons that we have to work with. We have to have at least one bond here. If we end up drawing valence electrons, that's going to be way too many electrons. We would have 3 electron pairs around the oxygen and 3 more around the carbon. That would give us a whopping 14 valence electrons. We don't have that many. So this is actually going to end up being a triple bond. And then we're going to have lone pairs on each of these. That gives us our 10 electrons total. And then to assign our formal charges, we look at carbon first. Carbon's got 4 valence electrons usually. This time it has 2 from the lone pair and then 1 from each bond, so that gives us 5. So carbon is going to have a formal charge of -1. And oxygen, just like we had over here, is going to have 6 normally, and it's going to own 2, 3, 4, 5, which gives us a formal charge of +1 in carbon monoxide. However, this doesn't mean that oxygen actually has a positive charge in the molecule. Oxygen is more electronegative than carbon, right? So it's actually going to be holding on to the electrons more tightly than carbon will. That's why I said that formal charge is a formalism. It's a way that we communicate where our electrons are, but it's not really, it doesn't really tell us the truth about how the electrons are distributed in the molecule. So you might say, why do we even use it then if it doesn't tell us how the electrons or what the truth really is? We will get to that later, but it turns out to actually be a very useful formalism. The last thing I'm going to talk about in this video is exceptions to the octet rule. So, like I mentioned briefly earlier, the octet rule is very nice, but it does not always apply. And there are many, many things in chemistry that we introduce as a rule to begin with, and later say that that rule is no longer valid and that there are many exceptions, or there's a wider thing going on. So our first exception is an odd number of electrons. So if we take nitrogen monoxide, which is another toxic gas that's produced in automobiles, it's a greenhouse gas, we have 11 electrons to work with, 5 from the nitrogen, 6 from the oxygen. So our skeleton, we have 1 bond at least, and if we take all of our lone pairs, two, 4, 6, 8, 10, 12, 14, that's too many electrons. Let's make one of these into a double bond. Now we have 2, 4, 6, 8, 10, And now we're just going to have a single electron on the nitrogen. If we look at our formal charges, nitrogen has 5 usually, minus 5 now is going to give us 0. Same with oxygen is also 0. However, nitrogen now has an incomplete octet, an unfilled shell. So this actually makes it much more reactive than it would normally be if our molecule had a full octet. But that is one exception if you have an odd number of electrons. Another exception is the set of electron deficient atoms. We've already sort of seen this with hydrogen. Hydrogen is not big enough and it doesn't have as many electrons, so it just can't maintain a full octet. It can only accommodate 2 electrons at once. But the same is true for other smaller molecules, smaller atoms as well, such as, like we glanced at earlier, this BF3 molecule. So boron only has 3 valence electrons on the periodic table. So it just can't, there's just not enough electrons to fill its entire octet. So we call this a sextet. 6 electrons around it. And let's mention that a lot of it's like boron, aluminum are very common in organic chemistry, and they a lot of times will demonstrate that property. The last one that I'll talk about is expanded octets. This is sort of the opposite. Something like sulfuric acid, H2SO4, will have an expanded octet, excuse me. So I'm not going to go through the entire process of drawing the Lewis dot structure or figuring it out, but we eventually find that it looks something like this. Let me fill in all our lone pairs. And we look at sulfur, and now it has 2, 4, 6, 8, 10, 12 electrons around it, which is much more than our expected 8. The thing is that sulfur is in the 3rd period of the periodic table. Because of that, it has access to more orbitals, which we will talk about briefly in the next video. And for now, we can say that it's larger than something like oxygen, and because it's so large, it can actually fit all of those electrons around it. So that happens a lot with sulfur, phosphorus, things like atoms like that are much larger. That was a brief recap of bonding and Lewis dot structures in organic chemistry. Thank you for watching Total Organic Chemistry, and I look forward to seeing you in the next video where I will continue this discussion with resonance and molecular orbitals.